Hi guys, today we'll be looking at multiple decrement table. So let's try to understand how to create a multiple decrement table. So for that, let's take a simple patience-based example where things will become slightly easy for us to understand. So let's say a person is active, and here we're talking about a death. So there could be a straight death, or there could be a possibility that this person might withdraw from the scheme, and after that death could be a possibility. There is a possibility that he had retired normally, and from retirement there could be a death. So during this retirement he's going to get the retirement benefit. Probably when he's going for withdrawal, there could be a separate or a return of premiums kind of contribution or kind of a benefit. Or if there is a death in active state itself, there could be other benefit that could be given, or it could be ill health retirement. So during the service he got the benefit from the ill health benefit, then there could be a possibility of that person might die. So this means that any of these states, the retirement benefit or some benefit will come in a traditional pension scheme. The contributions to the scheme, so here the contributions, they can keep continuing until the person is in an active state, and the moment he moves from the moment he moves from an active state to either the death state, there is some kind of a possibility. So for instance, for these two, there could be a regular pension that could come here under the death. It could be a one-time death in service kind of a benefit. Here there could be a kind of a one-time return of contribution kind of a benefit. So this is where I would like to know at what rate people are, or at what level I am moving from one state to the other, right? So this is the kind of a table we are trying to make, and this is what we are calling as a multiple decrement table. And towards the patient, if I'm making this multiple decrement table, I'm even calling it as a service table. And the way the service table typically gets prepared is that initially we choose the lowest we initially choose the lowest edge. So here we can have 20 to 22 to 25. So here I'll probably would like to find out the L20 number of people who are in that particular edge. So this I'll take it as a radix, just like the way we have created a single life table. Here also we take a radix, which is a very arbitrarily large number, so that the accuracy could be much better. And we are trying to find out the probabilities of, let's say, a transition for a person who's age X, the probability that he is transitioning from active state to withdrawal state, probability that he is transitioning from active state to retirement state, probability that from active state to ill health state, probability that from active state to death state. I can very well find out these probabilities based on estimation and graduation, smoothing all these probabilities. From there, I can very well compute my dx, which is nothing but lx times px, then ad, and d is for the depth. I can find out my wx as lx times p a w withdraw. Similarly, I can find out Rx as Lx times P A R. I can even find out Ix as Lx times P A I. And all these are the decrement that are coming up, which means that, so we got Lx plus 1, we have Lx minus of dx minus wx minus rx minus ix. If I remove all the set of people who have got decremented because of all these things, I will get for the next possible edge. And we also need to understand, if at all I'm trying to bring in the relationship, especially when there are no other transitions from that state, we are saying that px ad is same as aq x d also. So this will also become as aq x w for this other one, and then for this one it becomes aqxr and aqxi. So these are my dependent probabilities which I am supposed to compute. And how do I get into this service table? So for each of these causes, so we have seen that there are 4 causes. There's 1, 2, 3, 4. So for each of these 4 causes, I'm trying to come out with a single decrement table. So what is that single decrement? So there are no more AQs, so now I'm getting into a single decrement table, which only brings in that one single cause of decrement, and all others are non-operational. So this means that if the normal retirement is there only for the normal retirement and nothing else is operating, this means that I can very well come out as LX DX with retirement, QX only with retirement, all the other decrements are non-operational, PX only of retirement, others are non-operational, MUX all others are non-operational. This is what we are calling as independent rate of decrement, because they are not depending on any other aspects. So this means that we could take one linking function for deriving all this we can take a mu x of j as, I'll take it as mu x of j, which is where I'm trying to bring in the independence. And if at all, if I want to go with a mu x, we're simply talking about the summation of a mu x of j across all the j's. You add up all the j's, you are going to get the overall decrement of the a nu x, which is occurring because of any of the causes. And in this context, we also talk about a few other terminologies. So we talk about the AQX minus K. So this means that the probability that the life age X is leaving the population because of anything other than K. So we're clearly saying that the decrements excluding the decrement K, so which is as good as saying that I could very well say the overall decrement minus the probability of decrement that is coming purely because of K. This is what is represented as this. So the same logic for the actual number of deaths. So I'll call it as AD the total number of deaths, minus the deaths that have occurred because of K. So this is where our total number of lives that are left because of K. Now, if I'm removing out all the K's, whichever is left, that would be influenced by K. If I'm removing all, let's say if I'm looking at ADX minus K, these decrements, they actually occur on an average. All these decrements because of others, right? Because of maybe X up to X plus 1. If I assume that they occur on an average X plus half, I can talk about the decrements, all the K's being eliminated, some in the beginning, some in the end. So this means that they are still exposed to the decrement K on an average for half of the year. So this is where, if I have to compute the expected number of decrements purely because of K, so here I have to compute the expected number of decrements purely because of K. So the first thing, I'll look at it as ADX because of K direct, and whichever are exposed to risk because of non-K, ADX non-K, they are also getting exposed to K. So they are also getting exposed to K for half of it. So that's why I'm multiplying by half. So this will come out as the expected number of decrement exclusively because of K. So from here I can compute my Qx over K. So if I divide this entire thing by LX, so when you divide that by LX, what do you get? So our QXK, so here we're directly, or if I look at it the other way, if you take the cross multiplication and all, ADXK plus AD minus K x times Q K x times 1 over 2. So this is nothing but QXK. So this is equal to QXK times ALX. So from here, I take all the QX's to one side. So I get QX K times ALX minus of AD X minus K. And here we have 1 over 2. So this I'm calling as AD xk. So from here, I'm going to get my qx of k directly. So ad x because of k, divide this by a l x minus half times ad x because of non-k. So this is what I'm getting as the relationship. So minus of adx because of non-k. So if at all I'm talking about three decrements, and these are alpha, beta, gamma, I can get qx because of alpha is nothing but ad x because of alpha. Divide this by al x minus half ad x because of minus k because of, so minus k means because of beta, minus half ad x because of gamma. So this is as good as saying ad x alpha divided by al x minus half times ad x beta plus ad x gamma. So here I can very well pull out, or I divide across if I really want for qx. If I want for qx, then the same logic I can expand adx. Probably if I'm looking at if I divide this entire thing by lx, if I divide everything by alx, so this will become a q x alpha divided by 1 minus of what, and then we get a l x beta, sorry, aqx beta, and this one we get aqx gamma. So we get this because we are dividing by, so we divide all by alx. So after dividing this all by alx, you get the second part. So if I take the denominator to the numerator, so I will get aq x alpha, then 1 minus 1 over 2 times aq x beta plus aq x gamma, and this raised to the power minus 1. So if I'm 1 minus x to the power of minus 1 becomes 1 plus x to, like if you're using the higher powers, so I'll write this as aqx alpha to the power 1 plus half, and then we have aq x beta plus aq x gamma. So under the higher power scheme, the negative can be ignored. So this is the kind of relationship that can draw between AQX and QX, which means that independent probabilities versus the various dependent probabilities and vice versa. So we get Qx to the power alpha. If I really wanted Qx to the power alpha, I have already got it as Qx to the power alpha. If I divide it by ALX, it becomes AQx to the power alpha divided by 1 minus of half. 1 minus half AQx to the power beta. Qx to the power alpha will become 1 minus of AQX to the power of beta as per current scenario. And again, I could have taken it about saying AQX alpha times 1 plus half times AQX beta. That is a kind of a typical relationship that we are getting at this moment. Now, a few more important relationship. So we have APX, probability of survival for a person who's aged X up to N. That means no decrement operating. So this will come out like it's the same as NPX alpha times NPX beta and so on. So here if I take my N is equal to 1, then my APX nothing but PX alpha times PX beta times and so on. And this is nothing but 1 minus AQX. So this will write it as 1 minus QX alpha times 1 minus QX beta and so on. And so on. So this beta should be inside 1 minus QX beta. So if I take out this 1 minus, so this is becoming AQX directly is becoming as QX alpha. If I'm going with the minus of QX, so this becomes positive. So this becomes as AQX plus QX beta plus so on. And then minus pairwise. So when you get the pairwise, you get QX alpha, QX beta plus QX alpha, QX gamma, Q element. I'll get it as plus 3 elements, QX alpha, QX beta, QX gamma. So when you multiply 3 at a time, minus 4 at a time. So this is what the relationship is coming out depending on the number of risks that are there. If there are only 2 risks, obviously it comes out as AQX is coming out as QX alpha plus QX beta minus QX alpha times QX beta. So this is what is coming out AQX. Otherwise it's saying, but we're directly getting this kind of relationship also. And if I'm also getting AQX, especially under the assumption that uniformity in a single decrement table, if I'm going with an assumption of uniformity in a single decrement table, we know that x alpha is nothing but a dx alpha by a l x. So if I have to integrate this between 0 and 1 for a 1 year, whatever AL is there at x plus t divided by AL x times A mu x plus t. And now this, I'll take it as TPX. So this is equal to 0 to 1. I call this as TAP x times A mu x plus t. Now TAPX, I'll take this slightly multiplying and dividing TPX. So here I divide by TPX alpha, and then we have mu, then we have our A mu x plus t. So probably let me take only this part, TPX alpha times A mu x plus t. So this will become mu x plus t. TPX alpha, so TPX alpha times mu x plus t alpha. So this I can call it as qx alpha. So the top part, I'll take it as qx alpha. So TPAX alpha divided by TPAX alpha divided by TPX alpha. As I have already brought up the multiplication, so the integral becomes as TPX alpha times TPX beta and TPX gamma and so on. So if I'm dividing by TPX alpha, this becomes TPX beta, TPX gamma kind of style. So the final integration will become 0 to 1 TPX. So TPX beta, I'll take it as 1 minus TQX beta times 1 minus TQX gamma, and this part of TPX alpha mu x plus t will become QX alpha. So the same expansion is going to give me QX alpha times 1 minus of half times of QX beta plus QX gamma plus so on plus 1 by 3 times pairwise QX alpha, QX beta, just an expansion. So like this is going to work out. And again, if we are considering the situation of two ways, I get AQ x alpha is the same as QX alpha 1 minus of 1 minus of half QX beta. Similarly, our AQX beta will be QX beta times 1 minus half QX alpha. So from here we are getting one more relationship, QX alpha. So this comes out as AQ x alpha, and this is divided by 1 minus of half qx of beta. Earlier we've got the earlier we've got the expression. So this is where the difference is, if you can spot the difference. So earlier when I looked at this expression, I got qx alpha is nothing but aq x alpha. So this is divided by 1 minus of half aq x beta. But now under this situation of uniform decrement or uniformity in a single decrement, so this is directly coming out as aq x alpha divided by 1 minus of half qx of beta. So now you can see a small difference between the first one and the second one, and this is the difference that we are observing. And again, the simplification can happen in a similar manner, and what we see is that there is a similarity when we are going with the multi decrement kind of a table. So whether we're going with the multi state kind of mechanism, or we are relying on similar kind of this mechanism, we should end up more or less the same kind of a solution, because if I say x alpha, I will get it as the integration from 0 to 1 t ap x mu alpha dt, and we will directly get aqx. If we are simplifying it, we will get it as the natural log px alpha, and this is divided by natural log of apx times of aqx. So here we can rearrange the things. So qx, which would directly give us 1 minus of 1 minus aqx times alpha minus aqx beta. So this is raised to the power a q. So let me just write it properly. So we get 1 minus a q x alpha minus a q x beta raised to the power a q x to the power alpha over a q x to the power alpha plus a q x to the power beta. So this simplification will come out probably if you take up the numericals, and if you're using the multi kind of state approach, or if we are using the multiple decrement approach, as long as we are able to recollect, if we are able to maybe remember the formulas that are involved in the entire process, we can do the simplification and we can prepare the tables accordingly, right? So from the notes, there is a summary of the multiple decrement theory and construction of multiple decrement tables and the pension scheme service table. So there is a summary as well, and this lecture was just based on the multiple decrement tables, and I advise you to look up the calculations as well regarding the formulas, and you need to know and remember how to use these formulas. So thanks very much, and I'll see you in the next session.